Okay, hello everyone. I'm Alessandro, and on behalf of Alessia, Jacqueline, and Filippo, I welcome you to the discussion on gas here at GASPISA. So, as we all know very well, the evolution dynamics of the gas phase in galaxies is a very complex topic. So, to discuss it and analyze it, we decide to divide this discussion into three main subtopics. So, gas accretion, gas outflows, and gas and environments. For each one of those, we think of a series of open key questions that we would like to discuss with all of you in the audience, but in particular with some of you, on the basis of the talks that we have listened and the new interesting results that we have listened in the past days. But of course, every one of you is very welcome to enter the discussion and let us know your ideas and point of view. So if there is nothing else, without further ado, I leave the stage to Jacqueline, and I invite on stage the four people for this mini panel. You should have received the email yesterday. If not, this is a sort of surprise for you. So, Andrea? Okay, here we are.
Is Andrea here? Oh yeah, that is Simone.
Do you prefer to stand?
Okay. Where is Andrea?
Where is he?
Wait, we have only switch. Oh, there is the
Yes, this is the
okay.
fourth one.
Okay. Yes. Yeah. We were afraid it was too comfortable for you to sit, but maybe it is okay. So we all love this cold mode accretion, and some people think it really works. But we would first like to discuss, well, how does gas accrete into galaxies? Do we all agree? Do the simulations agree? On how so yesterday there were several talks. One was saying that if you look at the chemical evolution, it clearly and model the stellar populations, there clearly is we need accretion. But then there were also some people that said these cold storms coming in is very nice, but actually we know that the gas that has been accreted is more rotating with the galaxy. So is this an issue that we can discuss?
Yeah, I mean, I would say perhaps on the broadest level, I think there is agreement that accretion at very high redshift is so-called cold mode accretion, and that's probably coming in along filaments, although I don't think there's good consensus on the orientation of the filaments with respect to the galaxies. You say, are they mostly co-rotating, or are they coming in, off the plane, or even counter-rotating? And I think there's consensus that at very low redshift, you're dominated by hot mode accretion, which is probably more spherical, and is very susceptible to AGN feedback, virial shock heating. I think where simulations really do not at all agree is how you transition from one mode to the other, over what time scale that happens, what halo mass scale, what redshift. Those are still, I think, the different cosmological simulations really disagree quite a lot, depending on both the hydrosolver, the feedback scheme, environment that people are focusing on, and that's at least in part probably due to poorly resolved physics in the intergalactic and outer circumgalactic medium.
Any other comments on this? Yeah.
I mean, thank you, because I agree 100%. So, yeah, no, I mean, of course it depends which galaxy, what redshift we're talking about, what kind of galaxy. But in general, I mean, yeah, it seems like this switch between the different modes is it's not easy to model, but it looks like at least a low redshift, it's the hot accretion mode should be more dominant, and so you don't see. I mean, well, what I was trying to show in my talk, it's also like this, the cold gas coming in from the intergalactic medium. It's hard to get to the galaxy itself, at least for a Milky Way mass galaxy, but maybe not everyone agrees with this.
Okay, Jing really wants to say something.
Yeah.
Yeah.
From observer's point of view, I don't think the problem is resolved even at low G. And I don't think it's a simple question of the transition between hot and cold mode equation. I think what we have from the observational side is that we see cold gas there by some simple physical assumption. They may make it into the disk. They may survive for a quite long time. And as I showed the diffuse H1, by theory, it potentially can induce turbulent mixing, can, if it is high column density enough, can induce even directly thermal conduction-induced cooling. But the galaxies are complex ecosystems. They have feedbacks. Every time when I do the calculation, I do not take all these things into account. And on the simulation side, actually, we lack a guidance at the point. For example, the turbulent mixing picture I intensively use in my calculations are not incorporated in cosmological simulations at the moment, basically because the resolution requirement is too high. Yeah.
Yes, I want also to add that, in my opinion, when dealing with accretion, we are using the fundamental assumption that accretion is sort of universal and happening the same way for all the galaxies. But we should remember that the universe is very complex. Every galaxy has its own history. Every galaxy have made through a sort of interaction, have different AGN, different star formation history. So it could be that accretion is happening maybe in different galaxies. So not all galaxies are accreting. Not all galaxies are accreting at the same time. Maybe there is a preferential cosmic time where this accretion is happening in a way that we can actually observe it, because as an observer, I will say we still haven't found any evidence apart from the gas content in the universe that this accretion is happening now or at redshift 1, redshift 2. So I'm start to think that maybe asking how does accretion in galaxies take place, the first question, can be too much given the current knowledge that we have, because observationally it seems like we don't have the technology to do this. And modeling this would mean modeling many different processes that are occurring at many different time scale and spatial scale. So maybe we don't even have the computational power and the knowledge to do this. So maybe we should start to break the problem into small pieces and try to go for the most easiest approach and see if this works in the most simple case, let's say.
Can I make a question? Yes, of course I can.
Yes.
So you have shown a very impressive results from Mongoose. So what is missing from the observational point of view to prove accretion?
Well, given that unfortunately we are also proving that we don't have the support from the theoreticians, so we don't really know what we need. Maybe we need more sensitivity, maybe we need more resolution, and that's the problem, that only until now we can finally compare observation and theoretical model. Beforehand, the theoretical model were going in their way, trying to predict this accretion, and the observation cannot follow them. And so now we have the problem where observation finally managed to reach the detail of simulation, and we found out that they not match. So now we are going back to years and say, okay, then observation is what we need. And the problem is that I think there is also miscommunication between the two communities, because observers want to be always right, but also simulators want to be always right. So as we are seeing also during this conference, if I say we don't see accretion, then the question from a simulator is, are you really sure that you have your observation under control and there is some other systematic that is different between observation and simulation? And so in my opinion, what it's really important is that observer and simulator sit down together and try to figure it out a way so that simulation can predict what we actually need from the observational point of view to confirm that. Because right now, I can say, okay, let's build SKA because we want to go one order of magnitude lower, and then we put billions of euros and dollars in this project, and then suddenly we have no detection, so what next? It's not, then also go to the government and say, you give us billion of dollars for nothing. It's not good.
Okay, so maybe I have another question. So everybody likes to invoke the SKA to observe all this H1. My question would be, when would the simulations be capable of correctly predicting how much H1 there is? So that is below 10 to the 4, right?
Well, we're doing better now than we were before, but I mean, so there's been a lot of work in the last few years, maybe since 2019 or so, implementing these new methods to enhance the resolution in the circumgalactic medium in cosmological simulations. And some of these efforts have been truly heroic, and you do really see large differences. But the one thing that I think all of the models agree on is that the distribution and the level of H1 in the CGM and, you know, even in the cosmic web, when, I mean, we've done this experiment in the cosmic web as well, are not converged. As you increase the resolution, you tend to get more H1, and it's more widely distributed, and it's in smaller clouds, and we think we understand why that's happening, but where exactly the convergence level is and when we'll be able to reach it, I don't think there's any real consensus on. You know, it's definitely, I think we're at the level where it's worth starting to compare these predictions to observations, because we're definitely on the right track. But how far we are from the end, I couldn't tell you.
Thank you.
Yeah.
Yeah, sure. Yes.
So you started talking about the fact that simulations don't fully agree on the transition between the hot and the cold mode exactly. But there is a halo mass regime where that transition never occurs in some of the plots you were showing, which is the dwarf galaxies. Is that something the simulations agree on? And if so, is that maybe our best shot at detecting this cold accretion in the nearby universe? Because, you know, we've got plenty of dwarfs there.
Yeah. I believe it is. I don't think there's any discrepancy in terms of hot versus cold accretion on dwarf galaxy scales. I would say maybe playing off of that, I would say if we really wanted to look for consensus among cosmological simulations, one thing that we might do is, rather than trying to converge on the accretion of gas onto the galaxy, which is an extremely complicated problem, we might first verify that we're all converged and agree on the different modes of accretion onto the halo, which is a simpler problem, but is also, I mean, I don't think that that's fully converged as well in terms of the cold gas content of the cosmic web, the connectivity of dark matter halos to the cosmic web. You know, all these things are very intricate and involved, and I would be interested, I don't know, maybe Dylan knows more than I do about this specific subject, but I would be curious to know if cosmological simulations have converged with regard to the different modes of accretion onto the halo rather than onto the galaxy itself.
I wanted to make a short comment about the accretion, that our ignorance about how the accretion actually works is very, you know, it's a big problem, because in a universe where your galaxy is built by the compromise, by the interplay between accretion and the gas expulsion, if you cannot model properly the first, but you want your galaxy right, you need to put your hands on the second, and so you make prediction for outflow rate in galaxies that may be wrong because you cannot model properly the first.
Mm-hmm.
So this is modeling the first thing right is not a detail, it's fundamental to get the balance right.
100%.
No?
And I think that, I mean, that's why I advocated looking out at the halo, because I think you would be less, I mean, you would still be slightly sensitive to feedback, but the farther out you go, the less directly sensitive to feedback you would be. So if we can make sure that we're converged at the outermost boundary, then at least we have a starting point that we can start to talk about what happens, you know, further in and how that interplays with the ejecta and the outflows, as you just said.
All right, okay.
Can we, in case of the Milky Way, can we look at the stellar metallicity distribution? Because depending on when you dump and what kind of gas you dump into the disk, fresh gas into the disk, you change the gas metallicity and the metallicity that stars inherit from. So that could be give you a constraint on.
So certainly that's been something that a lot of simulators, and obviously observers as well, though I won't comment in detail on that, but certainly a lot of simulators have tried to do that, to use metallicity tagging to trace accretion. I think, to first orders that certainly works, but to second order there are a lot of complications there. As I mentioned yesterday, and others have talked about in the context of the galactic fountain, I mentioned it in the context of cold stream accretion. There's a lot of mixing that occurs, particularly in the inner halo. So even if the streams, beyond RVR were pristine, and I don't even think they were truly pristine there either, but even assuming that they were, by the time they hit the disk, they've already accumulated quite a bit of metals just by mixing with the CGM gas. So that signal might be diluted, and I'm not sure how to quantify it.
Elfie.
Maybe I leave my comment.
About whether we see accretion or not, there are not many cases, but a few ones are very indicative. And these are observations that I mentioned a couple of days ago, in which the evidence is that at redshift as low as 0.2 and up to 1 as well, the circumgalactic medium is co-rotating with the central disk all the way to a distance of 100 kpc, and as revealed by magnesium-2 absorptions on quasars. These are works by Crystal Martin, Ho, Boucher, Sable, and others. So whether the accretion is rain or whirlpool, I would say these observations indicate points towards ordered whirlpool-like accretion even at low redshift.
Okay, Filippo? I guess we need to move on, unless one of you still wants to say something very... Yeah, we have. Okay, thank you very much.
Excellent. So, the other direction of the flow. Please, the people mentioned here, come in, take a comfortable seat. So, I would like to try to involve the audience a little bit more. So maybe before starting with you, we can... these are the questions that we thought about. So how ubiquitous are gas outflows? We can, of course, for each of these questions, you can keep discussing for hours. AGN and star formation outflows, of course. And the last one is a bit related to really what is feedback doing to galaxies, right? That is always, does it really, here we're really talking about mostly ejective feedback. Does it really play a role in quenching and so on and so forth? So, the audience, do you have something to say here? Do you have another pressing question that we forgot? We have 15 minutes. We have to be. We will have a theory that works at any redshift.
Do you think it depends on redshifts? Just
yeah.
Yeah, it does seem to depend on redshift. Like what Letitia was showing, that people find like undeniable evidence of AGN feedback and actual gas outflows at higher redshift. This is something that people have been looking for in the local universe for years, and it's never been very clear.
Do you want to comment, Letitia, first? So I'm not sure, Ariel, if it is true observationally, because like in a local universe, we have a lot of evidence of really gentle flows that to me don't seem like too different from what Letizia is finding. I mean, there are evidence of, statistical evidence, I mean, using the Sloan of neutral gas outflows traced by the sodium or others traced by the emission lines. So I'm not sure that observationally we can state there is a difference now.
It's not clear that mass loading is the thing that evolves, but I think more likely it's that the incidence of star formation, high star formation rates and high AGN activity is what evolves, and that the physics of the outflow, it's not clear that that really cares a lot about what redshift it's at to 0th order. I think you can probably, do higher order changes by changing things like the ionization state of your gas or metallicity at higher redshift. But I think the bulk value of mass loading probably stays very close to the same across up till like redshift 5 at least.
Yeah, so more a physical effect on the star formation rate density, for example.
Because I think to second that, I think it kind of intermediate redshift, well, for me, let's say that means 0.6, which is now low redshift. You find very clear scaling relations with outflow velocity and star formation rate for star-forming galaxies. And so it could very well be that it's just that you have more high star-forming galaxies at high redshift. But one question is related to that third one, does the gas leave the galaxy? And there, when you go to high redshift, you have a lot more gas in the surrounding IgM. And so does that prevent the gas from actually leaving? Does the CGM look significantly different because of the enhanced density in the IgM? And I think that's really important to consider as well, not just whether or not you drive an outflow 2 kiloparsecs from the galaxy, but does it get out to 200 kiloparsecs?
Yeah, but let's see the opinion of the panel on this. I think it's very important.
I would say that I don't have answer, I have more questions. So what is the definition also in these questions about galaxy? So do we need that outflows leave the halo, dark matter halo, or just we need that outflows leaves the galaxy disk, if there is any disk, or so I think it depends on probably on the second question. So what is the impact of the outflows? I mean, if you think just matter enrichment or about the disk, how this with the metals in the disk, probably we don't need such powerful outflows that reach the galactic halo. And in that case, we just talk about intergalactic medium enrichment. I think it strongly depends on what is the impact of the outflows on the galaxy itself. And in this case, I mean, assuming that we have also faint outflows, I don't know how to define faint, because sometimes you say powerfully faint. What does it mean? In terms of velocity, in terms of mass loading factor, in terms of what? And even if you have a slow outflows, I mean, 100 kilometers per second, why you should not call it outflows? I mean, probably it's enough. And you should also take in mind that even if these outflows are driven by supernova at the beginning, such outflows are very fast because due to the expansion of supernova, and then they slow down. So it's not super easy to understand, to have a clear definition of the outflows, at least from my point of view.
Yeah, this is, I mean, this is a very important point, and just to give you a number, the galactic fountain in the Milky Way has a mass loading factor of 5 or 10, 5 to 10, right? It's impressive, but the gas stays there, right? So this is not the outflow everybody is looking for. Well, I mean, I'm looking for. I think it's very important.
Yeah, I would call it outflows that once.
There are several questions up there. Yeah.
I realize it's also a short panel, and this will be general, but one thing that's been on my mind this week, because the conference basically talking about is a caveat, or we hear the panel here is a function of gas phase, talking about it here, like talking about, especially in towards the third question, like we're understanding now just the difference of these outflows is just based on the types of gas we're talking about. I know we're talking about redshift and stellar mass and other things that we need to account for, but to be curious to hear a little bit more about the state of the art in that regard. Thanks.
Yeah. Does anyone want to comment? Alicia, you had something to say?
Yeah, I mean, I have a previous comment regarding what Stefano said about the definition of outflow. I think it's super important, I mean, because it depends on the scientific question that we want to answer. Because I don't know, for the cosmological point of view, maybe Dylan can comment on that. Probably we need outflow to leave the galaxy and to remove the gas from the galaxies, but maybe if we can call also outflows the fontaine. So I think it's really important to define what we want to answer and what outflows is in this respect. So if we want to compare the simulations, probably we need to observe outflows that are really going out to the halo. So for me it's important. It's not a matter of just a definition.
Yeah. So Diane, Rob, and then comments from the rest of the panel.
So I can respond to that very last point. In one of the Reichardt 2 papers, we compared directly to fire results, and we worked with Viraj and Drummond Fielding to, because they measure the outflow at like in a circle at like something like 50 kpc or something from the galaxy. And so we made a bunch of assumptions and sort of rescaled it to what would happen when you leave the disk. Because when we measure down the barrel outflows, when you do the decomposition, that's what we're measuring. That's what we're measuring, is gas that is leaving the plane of the disk. It's faster than the velocity. And we found that if you do that, and if you isolate the gas temperature to be basically the same, around 10 to the 4 Kelvin, their mass loading 0 point and scaling relations are very similar to Duvet values. And we also find very similar values to the warm gas, the same temperature gas for Tigris simulation. So, but if we were to try to say, like, okay, how much of the gas that's leaving a Duvet galaxy, which we've estimated, how much of the gas is actually making it to something like 30 or 50 kpc? In the ions, it's very little, or the optical ions, the 10 to the 4 ions. It's like, 1% or something. It's a very tiny amount. And so I think, like, what is an outflow? I don't like getting into definitions because I don't think galaxies care what we call them. But I think, yeah, just think about your physical question that you're answering and try to figure out where the problem is. And I think our real problem for understanding this part of the gas cycle is at the ions is where the gas, between where the gas leaves the disk and comes back down. I don't think we understand that. And I think it has to do with the multi-phase processes. I don't think we understand how the energy loading towards the colder phases, I don't think we understand that observationally. I don't think we understand how much cold gas wind is there.
Okay.
Yeah,
And
well, observationally, like, I also agree that maybe we don't understand, but for example, we can see the effects. So, for example, for our galaxy, we know that there are outflows and there are multi-phases, but probably they don't have the energy to actually, probably the ionized phase, which is faster, can reach the halo, but we have to see about the other phases. But the fact is that we do see the effect of these galaxies which are quenched, and some of them have been quenched for a long time. So for sure, even if we don't understand exactly then what is I guess where does this gas go, but at least continuously sustained outflows must do something to the galaxy. So this gas must not become stars anymore.
That is the question,
yeah.
right? Is it ejective or not? So I have Rob and Alvio. Rob, do you still have a comment? No. Okay, Alvio, and then we really want to hear from the simulation guru in the panel.
Okay, no, I'll be quick, I know that.
Just going on a broader context, if we look at clusters of galaxies, most of the metals are in the intracluster medium rather than in galaxies, by a factor of 2 at least, which means that these metals had to leave the galaxies. It's not clear a priori whether the metals were removed or ejected from the galaxies. But that's a constraint one has to look at. The other point is in favor of ejection versus extraction by ram pressure stripping, for example, which of course has to take place, is the fact that if we look at groups of 10 to the 13 or so solar masses of dark matter halos, then they are gas poor, indicating that the groups have ejected baryons. So this, to me, these are all observations, by the way, tend to favor ejection as the dominant, although not unique, way of having metals out of galaxies and into the intracluster medium.
Any quick reply?
I don't know if, I mean, probably the people that are working on environment can answer that better than me, but I mean, I think that it's kind of complicated, but I mean, there are
I think we can
solution
postpone it also to the next discussion. So, Rob, you did then. No. We lost him. Someone else. Or maybe, Stephanie, you want to add something to all the discussion.
Okay. I actually don't know that I'm the best simulator in this room to be at this table, but I think that this question of outflows is, we're finding kind of the same questions that all the observers are asking in simulations. And so this question of, how does the different mass loading factors as a function of this multi-phase medium move through the ICM, we're working really hard. And I don't know if the simulators agree with me, but I think that right now this field is very driven by observations, as most fields are really. And so the simulators are working really hard to try and match the observations. And so as we're kind of trying to compare among simulations, this is all kind of based in the idea of what can we do to try and measure our multi-phase medium in the observations. How far are our fountains going out, and how can we try and measure our mass loading factors down the barrel, just like observations are doing and other things. So right now, maybe my feeling is, I'm happy to be completely disagreed with, that simulations need kind of more observations to be able to better constrain what we need our outflows to be. Simulations find a whole range of different distances that outflows are going, and we're finding trends with galaxy mass, but it's pretty tough to continue a lot further until we can try and put kind of mock observations and observations on the same footing. So I think that's a large direction that simulations are going, and maybe Dylan's going to talk about that, I don't know. Actually, I hate it when people do that, because then if I don't talk about it, I feel bad. Anyway, I know that Dylan is doing that for TNG, and other people are as well.
Excellent. I think we close here. Carlo has something extremely important to say.
Extremely short. Last question. About whether it depends on redshift. Higher redshift galaxies are more compact. So the potential well is deeper, velocity pressure are higher, so the escape speed is higher. So you have to take this into account when not just the absolute speed, but also for given stellar mass, what is the depth of the potential well.
Excellent. Thanks. So thanks everybody and the panel.
So now is gas and environment. So please, these very nice people listed here, join me on the floor. You can stand or sit as you want. So this is the kind of question that we had in mind, but there could be many more in the audience, so please don't be shy. We can either start with the people in the audience or from the people here, as you want. And the kind of question we had was, how does the environment at the end affect the different gas phases, which are strict, which are enhanced? Do we understand the whole physics of the, for example, intracluster medium? We would like also to understand how efficient is every different process, and we are able actually to disentangle the different processes that can affect the same galaxy in the same environment. I don't know whether if we can or not. And what is the fate of the stripped gas? Well, in the case of round pressure stripping, it leaves the galaxy. We see it leaving. We see star formation ongoing sometimes. We kind of started to characterize this star formation, as Ariel was showing before. But there might be gas falling back in, and we need to understand everything to have a grasp on how the environment is affecting us. And last but not least, that's my opinion, we need to follow all the gas phases and at all the relevant scales. So that's my take, our question. Please give us your inputs or your inputs.
May I start then?
Yeah, of course.
So I'd like to stress that inflow and outflow processes are most important at high redshift to regulate the star formation and therefore shape the galaxies as a function of environment in the early universe. And inflow and outflow processes are the process that bridge, galaxy and the surrounding media, right, obviously. And so these are, by definition, the inflow and outflow processes depend on the surrounding environment, right? That's something that we should keep in mind. But the problem is that those processes are really hard to observe and quantify. Yeah. And so I encourage the theorists to make more direct predictions of the observable quantities such as metallicity, gas mass fraction, et cetera, as a function of environment to make a direct comparison, to understand.
On a positive note, I would say I would make an optimistic statement that at low redshift, in some cases at least, we are able to discriminate the different processes on the gas by a combination of integral field spectroscopy and multi-wavelength data sets, simply comparing what happens to the gas in the different phases to the stars, comparing the kinematics of the different components. It's hard work, it's painstaking, but it can be done. So I would say that at least in some cases, not always, but it's possible to discriminate between the different physical processes, which, as you say, in the end, all processes are, in a sense, environmental, in the sense that, environment, it's a word that we use in many cases without a real reason, but everything depends on where the galaxies are and how they're shaped in the beginning.
Jean?
I think in extreme conditions like the cluster, particularly near the core clusters, differentiate different processes, including environmental effects and internal effects, are relatively easier. But most of the galaxies, they hierarchically, they stay in lower mass groups, all the way down to the local group mass. There, I think one day we have to face this difficulty. We will not just addressing the question from a scaling relation, statistical indirect probe way. We will have to combine this GASP-like way with statistical group member galaxies to figure out the complex situation.
Do we have any inputs from the panel?
Yeah, I think I'd like to echo what Bianca was mentioning. In the nearby universe, I think we have quite a good idea of the kind of processes that occur, particularly in things like galaxy cluster. We're still lacking a lot of studies regarding things that occur in, for example, filaments and in the groups. But what we don't quite understand completely are the physics and particularly the time scales at which these different processes occur. And that's probably where we should probably be trying to put more of our efforts in the coming futures.
Yes, regarding the timescale, like we can know the phenomenon, what the yes, just like in GASPISA, we can see what happens when they undergoing these inflammatory effects. But it did where we need to know the timescale, we need to know the orbit, and observationally, this projection effects, it is currently the bottleneck when we need to interpret what happened to them. Yeah.
So for some galaxies, we know that they are quenched because they lack of a dense gas, and they fail to form a dense gas. But for some other quenched galaxies, they still have dense gas, but they fail to form stars. So I'm just wondering whether people have insights, whether the environment of some other specific processes that can help to distinguish these two types of situations. Yeah.
If I can answer? Well, we're having some galaxies that are, for example, extremely rich in molecular gas still, even after they have been kind of mostly stripped of their ionized gas. So my impression is that they keep the reservoir of molecular gas, which is not able to form stars anymore. So if you have a multi-wavelength data set, then you can start answering some of these questions. Well, if I can say something, I'm pretty aware of what GASP has been doing in the last year, so I think I agree with Bianca that we start knowing a lot of stuff. But what I was asking myself, listening to the talks in these days, is that, for example, in Virgo and in other clusters, the situation that we have in GASP seems to be different. So my question was, do we actually understand how RAM pressure works in clusters with different masses, different velocity dispersion, and does it affect the behavior or the quenching of different galaxies with different masses? Because I think we are seeing different things in our sample of clusters, which are mostly low velocity dispersion clusters with respect to Virgo. So that's a call for Luca, actually.
Thanks, Alessia. Look, I don't think we are seeing anything different, if I can be completely honest. I think at GASP, correct me if I'm wrong, by selection you have identified pre-selected the very extreme cases of RAM pressure stripping. You knew, even before getting the Muse data, that you were going to get these beautiful tails.
We hoped.
Yeah. But so this is a fantastic data set to understand also what Stephanie was mentioning, all the physics when you have these extreme cases of RAM pressure stripping. Then the question, I think, is how often we have these extreme cases. It's not whether we have RAM pressure stripping or not, is when we have the tail that is lit up. In star formation, we were having a conversation over coffee of what's actually the fraction of the population of satellite galaxies, let's say across a 10 to the 14 halo masses that are really star forming. And I don't think observationally we have the answer to that yet, because we have a very small sample of galaxies to look at this. And then going back to what Jean was saying, the point is that, look, Coma is super rare. Virgo and Fornax starts to be okay, but if we go back 20 years ago, all the work from this one Digital Gas Sky survey about quenching and everything, everybody was claiming, oh, RAM pressure, you don't care about RAM pressure at all. And now it's so fascinating for me, who was a PhD student at that time, how now the community seems to have flipped the table. I don't think it's one or the other, a bit, but I think we have a problem that when we go to a 10 to the 13 halo mass group, I would argue we know that you have stripping of gas, but what physical processes are at play goes back to the time scale, because the RAM pressure is significantly slower acting than we see in clusters.
There's a question there.
Whoa, I triggered a lot of questions. Great.
The guy behind. You want
just
to...
to follow up on what Luca said, the problem is that it's not just a matter of, halo mass, because Virgo is more massive than many of the wings GASP clusters. So the problem is much more, it's much more complex than that. And even in groups, we do see groups where in the same group, Benedetta has these examples, you observe simultaneously different processes. One galaxy that is run pressure stripped, one that is starved, one that is, in the same group. So it's much more complicated. We cannot just say, run pressure is only for the high mass clusters. This is wrong. We see exceptional jellyfish cases in small, very small clusters in groups.
Good. Good.
Just wanted to say that if only there was a simulated sample, a very, very large simulated sample of jellyfish one could look for, then you could answer some of these questions about how scarce they are, and this is a build-up to my talk tomorrow. But stealing my own thunder, I will say that one of the things we discovered, for example, is that while, of course, clusters have the highest fractions of jellyfish, most jellyfish galaxies in our simulation were actually in groups, because there are that many more groups. There's a lot more groups around, and almost every group will have, most groups will have at least one jellyfish. And so most jellyfish in the universe are probably in the group scale.
If I can just, I'm very familiar with your work, that's great. Just 2 comments. When I talk about jellyfish, I'm talking about when you have star formation in the tail. So if you only have a gas tail, then we have jellyfish all over the places. Even the small and large Magellanic clouds are jellyfishes.
So two different things. First, I thought it was very interesting Mapati's talk where she talked about how you could enhance the susceptibility of galaxies in different environments to ram pressure if they had tidal interactions with other galaxies. And so that's something where the tidal interactions in groups are going to be more enhanced than in clusters. So it can enable ram pressure in environments where you wouldn't normally expect it. I think the other thing is that all of these really detailed multi-wavelength, high-resolution, multi-phase investigations are great at Z of 0.0002, but once we start getting into like things beyond 0.2, 0.3, 0.4, all of this becomes much more difficult, and yet much of the environmental quenching happened there. So this is again echoing this call that Taddy made, that we need lots of good predictions for things we can actually observe, like star formation rates, metallicities, gas fractions, and like outflows as we can measure them. So what are the outflow speeds we expect from down the barrel measurements? What's the neutral gas outflows from things like sodium D? I think those are all things that we need a lot of predictions for, good predictions.
Last, I think, right? No, maybe too short.
Very quick, I just wanted to say that there is something we are ignoring because it's hard. It's the orbits. I mean, we are neglecting completely that galaxies can enter into the same clusters with different velocities, different orbits, and so their history can be completely different simply because ram pressure stripping can work in the same way, but it really depends on how the galaxies infos. And it's very, very hard. I know that Andrea will talk about this tomorrow, but I think it's something we should try to put more, today. To put some more effort to try to understand what to do with the orbits information.
Luca, dai.
Look, just to say I fully agree, but this goes back also to what Bianca was saying. If we go back 20 years ago to the beautiful work by Bernd Vollmer, when you have this kind of data and you plug them in with the simulation, you can actually reconstruct the mechanisms that are at play in the orbits. So there is hope.
Marco, do you still have your question? Short? Dai.
Well, first of all, a comment. You said that the environment is multi-dimensional, something like that.
Probably,
yeah. No, I mean, it's right in that direction. So parameterizing the environment just with mass doesn't make a lot of sense. Also, the dynamical states matters a lot, also for ram pressure stripping. So whether you have a relaxed cluster or not, then the situation, the properties of the ICM change a lot. So also the efficiency of the ram pressure, for example, and other environmental effects change a lot. then what's, yeah. So you said, Patti, that it's way more difficult to study what is going on in filaments, for example, and something that was said a couple of times. So maybe it's more difficult simply because it's more expensive observationally. So the question is, why don't we understand clearly what is going on outside cluster, or worse than what is going on in clusters, just because of observational limitations?
Partly yes, but I think it's also quite difficult to disentangle the actual filamentary effects from the groups that are in the filament. So when you're looking at galaxies being affected by the filament, is it just the galaxies within the groups as they move through, or is it the actual filaments, like the spines of the filaments, that are affecting those galaxies? And I don't think we found a good way to disentangle the two yet, fortunately.
Tomorrow there will be a panel on environments.
Yes,
follow
and
up
the
on that.
filament people will talk about it, possibly after this session. So, yeah, I think we need to close up, right? Yeah, okay. So, thank you all for participating to the discussion, the speaker, the mini panels, everyone. Thank you so much.
Perfect. Thank you. I'm going to be perfectly on time. Maybe not. Maybe not, yeah. We'll see how it goes. Thanks. Yeah, so this is actually going to be just kind of a great continuation of the discussion and throw a bit more fire on the flame. So first, let me thank the organizers, Bianca and everyone, for the great conference so far. I've been asked to give a bit of perspectives on the galactic baryon cycle from the point of view, right, of cosmological hydrodynamical simulations of galaxy formation. For those who have met me, my name is Dale Nelson. I'm at Heidelberg University in Germany. So let me start a bit gently. Simulations of the baryon cycle, of course, there's many different computational approaches, right, at different scales, depending on what you're trying to study, starting all the way from small individual little clouds to these tall box patches of the ISM simulations to idealized disks. We've heard a lot about idealized disks, also in wind tunnels this morning, all the way to idealized global halos, more often in the context of jets and AGN feedback, up to cosmological zoom simulations, right, individual galaxies, and then the large boxes, large volumes. These are projects like Eagle, Simba, TNG, Horizon AGN, Astrid. You've heard of them. I'm going to focus mainly on the right side of this panel, where indeed there's a bit more of a focus on statistics, on populations, and how we can connect galaxies, right, to their larger scale environments. In these kinds of large volume simulations, this is what galaxies look like these days. So this is just a gallery of stellar light images from TNG 50. There's disks, right? There's ellipticals, there's mergers ongoing, there's warps, there's bulges, there's bars, there's all kinds of morphological diversity and complexity, all just emerging, right? All these galaxies appear in the same simulation with the same physics. And we want to start to understand, of course, what's going on. And what these simulations allow us to do, I really want to emphasize, is connect what we see internally in the structure of galaxies to flows of gas, to the baryon cycle on larger scales. So let me zoom out a lot and show you a cosmic web, 100 megaparsecs or so from top to bottom. Right, so all those galaxies we just saw there inside of individual pixels, right, in this image. Extraordinarily small, but what we can do with these simulations is make this connection, right, between the ISM scales out to the halo scales and out to the IGM and the accretion scales. And of course we know a lot from these simulations. Physically, we know about the dark matter here. This is the gas density tracing the dark matter. We know about the velocity, lots of feedback-driven velocities you see here, very high. Of course, where the stars form as a stellar density, temperature, the thermal state of the gas, Metallicity, of course, the enrichment processes. This is Mach number of shocks. This is magnetic field strength. This is X-ray emission predictions. Lots of information, right? Especially about the gas. And again, I just want to emphasize this point, right? This strength of these large volume cosmological simulations is really, I think, to make this connection between what's going on across scales, gas flows, and how these flows build galaxies. Great, so the question is, how do galaxies get their gas and how do they get rid of it? This is my schematic intro very quickly. We all, I think, appreciate this point. So you have a galaxy, it sits in the center of a halo. If the halo is big enough, or no matter how big the halo is, of course you have cosmic accretion coming in. If the halo is big enough, you form a hot halo, you have a virial shock maybe. This has a kind of global cooling perhaps. Also maybe you have more localized cooling phenomena going on. Then of course you have satellites and mergers, possibly restricted in their baryon cycle in interesting ways. You have winds, right, feedback-driven outflows from the galaxy, and thus recycling and fountain phenomena also occurring, of course, in satellite galaxies if they still have their feedback. This is the baryon cycle, this complicated mess, of course, and it takes place in the CGM, which depends very strongly, I want to emphasize, as we were just discussing, on mass and environment, right, all the details of these processes. So I want to show a movie, because the baryon cycle, how a galaxy gets built in one of these simulations, is super messy. And I want to emphasize it with a movie. We're just watching one galaxy get formed over time. You see redshift up here, redshift 4. This is going to be about a Milky Way by redshift 0. And at high redshift, the main panel is gas density. It's just a mess. Right? You don't really see a galaxy. I see lots of accretion coming in from the intergalactic medium, from larger scales, forming this kind of swirling, turbulent ball of messy gas in the center. This is a large-scale view, zoomed-in views of the gas and the stars. We're approaching redshift 2, and at some point, the flows around this galaxy start to kind of settle down and in their angular momentum content, and what you see is the emergence of a disk. Right? We're kind of looking at it edge on, and it's just appeared at some cosmic epoch, depending on the mass scale. Now we freeze a bit, spin around, so there you see the disk kind of face on. The left-hand panel in the green is the metallicity, right? Just to emphasize that this baryon cycle of gas flows has brought in a lot of gas, brought out a lot of gas from feedback, polluted the CGM and the whole near-field IGM with metals. Then we'll let the movie play. This is a pretty boring galaxy. There's no major mergers, right, after redshift 2 or so. It's just kind of a spinning disk in isolation. But if you look, you see lots of outflows, right? You see the stuff getting blown out, and you see it coming back. There's a big explosion of stuff going out. You see some preferential directions, right? You see a lot of accretion in the disk plane along what we would call the major axis directions of the disk, a lot of outflows along the other directions, the minor axis of the disks. We'll come back to this. I don't think I have anything else to say except this is the baryon cycle in action, right? Outflows, recycling, and inflows. Good, so the question is, how does gas cycle in and out of galaxies from the perspective of the simulations? And I want to start a bit with outflows. Outflows are very strong and very important in current cosmological galaxy formation simulations. So this is an example of an AGN-driven outflow. It's coming from a galaxy which is edge-on. It exists in this little square. I've zoomed in on it here, so that's kind of the disk, gas disk of the galaxy. And the black hole, you see it there, at this super small scale, is driving this enormous outflow. You see the scale bar here, hundreds of kiloparsecs. In extent, it looks kind of like a cocoonish morphology bubble moving outwards. This is overdensity shells. It's dragging highly enriched gas, right, from the disk out to 100 kiloparsecs. This is supersolar. In yellow, this is a big galaxy. Very fast, right? Thousands of kilometers a second, even at tens of kiloparsecs away from the galaxy, and very hot. So a very hot over pressurized bubble. This is a AGN feedback in action. It's very anisotropic, right? It's not a spherical shell moving out. We'll come back to this. Let me show you another example, smaller mass scale. So this is a stellar feedback driven outflow. It's just a smaller mass galaxy. The virial radius is this outer circle, I believe. So we're quite zoomed in. Again, the galaxy is kind of edge on, and you see some streamlines of velocity. You see outflow preferentially, again, along the minor axis directions, and you can also see the inflow coming in where the outflow is not blocking it, right along perpendicular directions. And this is quite actually an interesting and strong signature, which is that although we inject all this energy, from the supernova feedback, the stellar feedback, in a purely isotropic way inside the galaxy, we see this natural collimation, this natural kind of confinement of outflows along preferred directions. So this is angle, if you're spinning around a circle in this direction, and distance, and color showing you the outflow rate, how much stuff is actually moving out. What you see these big yellow features along the minor axis directions, right? Just quantifying this collimation of stellar winds in this case, where we also see in black hole-driven winds. This leads to a pretty interesting observational prediction. This is not yet observed. This is a signature in the gas metallicity, although I don't write it, at 100 kiloparsecs away from the galaxy. So in the circumgalactic medium, that the gas metallicity should depend strongly on the angle with respect to the galactic disk. So here you have the major axis direction, right, where you have relatively unenriched gas coming in, and then the minor axis direction, we have relatively enriched gas going out, which gives you this azimuthal angle dependence on the gas metallicity basically throughout the entire circumgalactic medium. Let me show you a few more properties about outflows and how this part of the baryon cycle works. The first is that outflow velocities are large. They get larger with mass. This is probably not a surprise to anyone. Outflow velocity, you see some of the typical numbers as a function of stellar mass from 10 to the 8 to 10 to the 11. You can look at, say, the orange line, 95th percentile, just to get a sense of how velocity gets much, much faster for bigger galaxies. If you look at the distribution of velocities, right, lots of gas is moving out at different velocities. Low mass galaxies, these lines here, they have these kind of compact velocity distributions of their outflows. And then when you get to massive galaxies, the brown and the pink lines here, where the AGN feedback starts to kick in, you see the emergence of these very high velocity tails. Right, this is when gas can start moving much, much faster than a few hundred kilometers a second. You might be worried how these velocities are getting pretty big. Let me just put on the Milky Way here, and the median outflow velocity of what a Milky Way would have in these kinds of simulations. It's actually not very high. It's about 100, 150 kilometers per second. This is at a distance of 10 kiloparsecs away from the disk. Let's talk about the mass loading, right? This also came up in the discussion, just the mass outflow rate divided by the star formation rate of the galaxy. So this is mass loading, again, as a function of mass, and it drops, right? You can focus on the blue line, if you like. It drops from very high values for dwarf galaxies. This is a common feature of current cosmological simulations, values up to 100, down to values of a few for a Milky Way. And then there's actually this inversion, which is quite interesting, this upturn, where AGN feedback again starts to play a role and drive very powerful outflows, although the star formation rate of these galaxies is quite low. This is what causes this inversion. So this is a picture from the illustrious TNG simulations. I want to make a comparison to Eagle, right? Another simulation, very different feedback physics in this simulation. These two blue lines are essentially the same. They're from TNG. And in yellow, you see Eagle. And we've added another dimension to the problem, which is the distance away from the galaxy that you're thinking about, 10, 20, 50, or the virial radius, right? Going farther and farther away. So actually, the simulations disagree. That's what I want to emphasize here. And in particular, Eagle starts to show similar behavior as TNG only when you go far away. So only in these dotted lines, only when you get farther into the halo, which is a sign that as outflows move out, they're entraining material and actually gaining mass, right? So this is somehow an important commentary on the fact that the feedback is working quite differently in the ejective versus preventative debate, right? So TNG you could think of as very ejective. It's pushing a lot of stuff out of the galaxy from the beginning, whereas Eagle is pushing not much mass out of the galaxy, but actually more mass out of the halo as you get farther away. So as a function of distance, the outflow properties are quite different in these simulations. It leads to very different recycling, right? If you imagine the recycling fountain, its strength or its size, it's very different in different simulations. So these are the two plots we just saw, mass loading factors versus stellar mass. I want to give two more perspectives here. This is fire, this is the Nihao simulation, same exact plot, right? So versus stellar mass loadings are getting smaller, right? As galaxies get bigger, they all agree. In simulations which have black holes, which are the two on the left, right? Not these two, for example, you see this inversion of the mass loading factors, but they're just monotonically decreasing if you don't have black hole feedback involved. And versus radius, I want to emphasize this. It depends strongly on the model, and I think the models give quite different answers, which is to say how the outflows actually propagate
throughout the halo is telling us something important about how their physics is operating. And this is reflected in how much gas is actually left in the halo, how much gas you throw out completely, or you could say the gas fraction of the halo. As was mentioned, and we'll come back to this. One super quick word on redshift, as we were also just discussing it. So outflows are much stronger at high redshift, at fixed mass. This is the statement from the simulation. So this is from the Horizon AGN simulations, outflow rates versus stellar mass. On the right, I'll put outflow velocities versus stellar mass. The different lines are different redshifts. So you pick a mass, go vertically upwards. You see that as you go from redshift 0 to redshift 2, 4, 6, outflows are much faster, and they have more flow, right? The flow rates are higher. Good. Let's talk a bit about metallicity, right? So there's also a metallic baryon cycle as the metals are moving around. This is the metallicity of outflows, again, as a function of mass. It goes up, of course, just because the mass metallicity goes up. Fine. But if you normalize by the metallicity of the interstellar medium, so of the galaxy that you have, what you see is that outflows in this particular simulation tend to be slightly more enriched than the galaxies they came from. That's outflow. There's also the metallicity of inflow, of course. Let's think about what's coming in across the virial radius, as we were just discussing, so onto the halo itself. Right, so the metallicity of that inflow relative to the galaxy, again, is quite low, as you would expect. But as you go closer towards the galaxy, so we move down to a quarter of the virial radius, the metallicity is much higher. This is maybe a bit of mixing and entrainment with the CGM, but I think it's more so reflecting the fountain. And the fact that what you see here as inflows at this distance, right, is really recent outflows which are recycling and coming back, and thus they have quite a high metallicity. Good, I showed you lots of numbers, but I want to emphasize that the structure of these flows is very complicated. Spatially, it has lots of structure. So this is eight different views of a circumgalactic medium of a Milky Way-like galaxy on the scale of the virial radius here. We have gas density, temperature, pressure, entropy, H1, metallicity, O6, and X-ray luminosity. Observables more on the right. This is from Ramesh in TNG50. And I just want to emphasize that, especially when you start to think about accretion and inflows near the galaxy, they're clumpy, right? They're not just a smooth, it's not just a number, they have a lot of spatial structure. And what we've begun to appreciate more and more is the importance of this small-scale structure for the baryon cycle. So this is just a rotation movie. We're frozen in time. It's a Milky Way-like galaxy at redshift 0. It's showing you metallicity. You can see the disk, right, when it comes in kind of edge on. And what you see is accretion, so a satellite galaxy getting stripped and has a low metallicity, huge tail behind it. You also see outflows when the disk comes edge on. You start to see kind of head-tail morphologies of little clouds getting blown out away from the disk. This is coming from this series of, or from a family of simulations which Nir alluded to, where we're intentionally increasing the resolution, not in the galaxy, but in the diffuse gas in the halo which builds the galaxy, which people are starting to explore more and more. And when you do that, that lets you zoom in and see really small-scale structure in the baryon cycle, in the flows. So this is a zoom in. The galaxy is here. This is, again, the virial radius. We're zooming all the way down to this kiloparsec panel. We see the emergence of these little cold clouds, right? Thousands, tens of thousands, hundreds of thousands of little discrete cold clouds which are actually participating in the baryon cycle, right? They're inflowing to the galaxy, for example, and feeding the star formation rate. We can start to explore interesting physics like the magnetic fields and what they're doing. So the streamlines here start to show you the magnetic fields because we've found that magnetic draping, right, when the fields wrap around the clouds, can actually be important, can let them survive, can let that cold gas live longer. This is an exact analogy, right, to jellyfish galaxies and jellyfish tails and the effects of magnetic draping. This is my excuse to flash this result from Eric Rohr, right, which is the an investigation in TNG50 of jellyfish galaxies, but looking again, as we were just discussing quite a bit, the duration of REM pressure stripping, right? So how long do satellites show evidence of REM pressure stripping? And I just want to emphasize these are extremely long timescales, right? It could be anywhere from a billion to 10 billion years where a satellite galaxy has ongoing REM pressure stripping, and you see the halo mass here. So as you go down in mass, actually from the clusters, more to the groups, more to the Milky Ways, you tend to get longer periods, right, of ongoing REM pressure stripping. I'll skip the details. I'll just, again, highlight Elad. We'll talk about this more tomorrow morning. And if you didn't see Charlene's poster earlier this week, go talk to her about the AGN activity in these jellyfish. I want to zoom out a little bit because what was also alluded to in the discussion is the impact of the baryon cycle on the total gas contents of the halos, right? So we know, as was pointed out, that halos don't have the total amount of baryons that they should, right? They're deficient, so if you're asking about what's the gas content relative to the dark matter content, we would expect that to be a fraction of 0.16, right? The cosmic baryon fraction. But if we plot gas fraction of halos versus halo mass, observations tell us, especially X-ray observations of groups and slightly more massive systems, tell us that we're far below this cosmic line, right? Halos are missing a large fraction of the baryons they should have. And simulations agree. So this line is the fiducial result from the TNG simulations. But it depends a lot on the physics that you're including. So if you turn off the magnetic fields in blue, or you turn off stellar feedback, or delete the black holes, you significantly alter the gas contents of halos, right? The halo scale gas fraction, basically what you can still keep inside of your halos. So I want to show you a picture of this again. This is a picture of gas density, but in a way you've probably not seen it before. It's normalized to the cosmic fraction. So wherever you see white, then the gas density at that location is what it should be. It equals the cosmic baryon fraction. Wherever you see blue, we are deficient. We're missing what we should have. And where you see red, we actually have an excess. So this is a group, right? 10 to the 13. This is the virial radius. The entire halo is strongly deficient in all the baryons it should have had given its dark matter, except for the little red dot at the center, of course. That's the galaxy, baryon-dominated galaxy. And if you squint, you can almost see kind of a pile-up, an excess of red at larger scales, 2, 3, 4 times the virial radius, right? This is where the baryons have gone because they've been pushed out of the halo due to feedback. So we can measure that scale. We can measure how far out do you have to go to find all of the baryons to close the halo, to find, that it should have been associated with the dark matter. We call it the closure radius. It's defined very simply, again, the radius within which the baryon fraction equals the cosmic value, the closure radius. This is the answer. So in units of the virial radius, from 1 virial radius up to 20, the closure radius is a function of halo mass, all the way from microscopic dwarf galaxies, Milky Ways, groups, clusters, right? A very large range on the x-axis. This is the TNG simulation. So stellar feedback here is losing to gravity. That's why the outflows are not going as far. The baryons are closer to the halo. Then this is the onset of strong AGN feedback, this upturn, where the ejective nature of baryons goes out to quite larger scales. And then again, gravity wins. You get down to clusters, eventually to closed systems. This is very different in different models. This is the interesting point, right? So here is the Eagle simulation and SIMBA simulation in purple and green. They have very different models for feedback physics, and you see it reflected in the impact on the baryons, right? How they move on large scales. So SIMBA in green actually looks quite a bit like TNG, the same shape, but offset to much larger values, right? For Milky Ways, you might have to go out to 15 times the virial radius to find all the baryons which were in the halo, or would have been there without the AGN feedback. Eagle doesn't have this bump, right? It's monotonically decreasing. It has a very different way of implementing black hole feedback. So this is perhaps an observational tracer in the future of the large-scale impact of feedback on the baryons. In the last 2 or 3 minutes, I want to advertise something new, which I think is quite relevant this week, which is, as this arrow suggests, what do we put in this big empty space here? So this is just our newest simulation project. It's called TNG Cluster. As the name suggests, it's simulations of clusters and their galaxy populations. So it lets us study galaxy evolution in the densest environments in the universe. What it is a suite of about 350 really massive galaxy clusters, exactly illustrious TNG. Nothing has changed. Most importantly, not the resolution. So these are very high resolution simulations for clusters, which lets us look at the satellites and satellite evolution. The halos of these clusters, they have a diverse baryon cycle themselves. And I'm showing that to you here in terms of cooling times in the centers of these halos. This is this debate between cool core and non-cool core. And I just want to emphasize that as we look at this sample across the different ranges of the host halo masses of the clusters, we always see both non-cool core systems, so that means low density, that means the central galaxy is not getting fueled by any new accretion, any cold gas. And likewise, the black hole is not getting fueled. Through weak cool core systems and strong cool core systems like Perseus with the cool H-alpha filaments, where the central galaxies really can get fresh supplies of gas, right, for star formation and for AGN activity. So yes, this is maybe the baryon cycle of clusters themselves, but let's talk about the satellites really quickly. There's lots of satellites. This is just richness versus halo mass. So these systems can host hundreds, right, of bright galaxies each. They're very rich. And if you look at smaller mass galaxies, 10 to the 9, they could even host thousands of satellites in a single cluster. And we can look at them because we have enough resolution. So in the last few slides, I wanted to show this result again from Eric Rohr, which I think is kind of interesting and touches on the discussion we were having. It's about stripping of satellite galaxies, and in particular, the fact that they can often retain their circumgalactic medium, the satellite. So let me show it to you. This is an X-ray image of a cluster on the scale of the virial radius. What you mostly see here is the ICM, is the cluster itself. We don't see the satellite. So we want to subtract off the background. So we make a smooth model, and then we subtract it away to see what's left. This is the residual, right? So yellow is 1, that's the background. Blue means in excess, higher X-ray emission, more gas. Red means lower, right? Less X-ray emission, less gas. And you start to see at the locations of satellites, well, they just pop out visually. Why? Because around satellite galaxies, even at the virial radius, or even within, you see an excess of gas around them, right? Which means they've been able to hold on to their hot halo gas, which is emitting in the X-rays. You can then plot, say, the excess of the X-ray. X-ray is just, again, a tracer of the hot gas, as a function of distance away from the satellites, from the center of the satellites in the clusters. And you see this kind of excesses can be factors of a few, up to a factor of 10. And indeed, this is the quantitative result. So stacking on stellar mass, right, of the satellites, what you find is that for the most massive satellites, the really big guys, which can only exist in clusters and still be called a satellite, you can see that they have a factor of 10 to 5 to 10 excess, right, of their X-ray surface brightness out to tens of kiloparsecs, basically, which is, again, maybe an observational probe of how the stripping or how the baryon cycle is working as a function of galaxy stellar mass in these really, really dense environments. Good. That brings me just to take-home messages. So first of all, in the very broad picture, that what these hydro simulations allow us to do in these large volumes is to connect, right, the internal details of the galaxies to the large-scale flows which have built them up, in particular from about 100 parsec scales, that's where we are at best, up to, you know, the 10 megaparsec scales at total Lagrangian regions which ever build a galaxy. And as I try to emphasize, it's not just a number, it's not just a mass loading factor, but we can spatially resolve the flows and where they are, and say if they have these angular or azimuthal angle variation signatures, which are often quite interesting. And I've highlighted a few observational phenomena which are related to the flows of gas outside of galaxies, which I think, as we were starting to discuss, is a very interesting regime to compare with observations and thus constrain the models, because the models are typically built and constrained around the properties of galaxies and not what's going on outside of galaxies. I'll stop there. Thank you.
Hi, Dylan. Great talk, as always. I was wondering, when you were showing the slide which compares the TNG and Eagle, and you said that the relation agrees between these two simulations as we go farther out for the outflows. And this reminded me of a point that we were discussing during the discussion session, that we should see if simulations agree on the inflow onto the halo first rather than the disk. So my question regarding that bottom left panel is, do we see similar agreement for the inflows as well as we go farther out?
Yeah, I don't have the paper in mind, the plot in mind, which really compares this. I'm not sure it's been done, to be honest, this comparison of accretion. This Mitchell work did the comparison of the outflow in a very apples-to-apples way. So I think there's two parts to this agreement. One is details of the computation and of the numerics, which in the past was a big problem. Then maybe the accretion, how the inflows are working, how the streams are surviving or not. This could be really strongly affected by the numerical details. Maybe we're getting a better handle on this, maybe not. The second aspect is the feedback models, right? And all the different simulations have very different feedback models, but this is not just outflow, right? This material goes out to large scales, especially at early times, and it sets all the accretion, subsequent inflow, for the rest of the universe of these objects, right? So I think that these two are very intertwined, and because the outflow and the feedback models are quite different, I think even the accretion under the halos could still have interesting differences, physical and numerical.
Thanks.
So about this very small baryon fraction that you see within the virial radius of halos, is that consistent with what we know about the CGM from X-ray measurement and absorption line measurement, like the COS halos project?
Like this panel.
Well, when you show that basically the baryon fraction within the virial radius is very, very small, and you need to enclose up to like 10 times the virial radius to, get the baryon fraction.
Exactly. So this is the baryon gas fraction
Yeah,
in
okay,
the
yeah,
virial
yeah,
radius.
sure.
And then the question is, how far out has all the material gone? If it's left, fine. So this is observations. The point of this plot is maybe that this entire region is blank, right? Which is to say, observationally, there is no census, total baryon census within halos below the group scale. It's simply impossible because we do not have a handle on the hot component, which is by far the dominant and most important component, even say for the Milky Way mass regime, right? Because it's too faint in X-rays. So there's another version of this plot where instead of varying the physics of TNG, I put other simulations, right? I put Eagle and I put Simba. They're crazy different actually here. And it's very impressive to realize that we do not have the observational constraints to actually choose between these lines. That's what I would say. It would be great to improve that situation.
Just about this, I would say, this is very interesting, by the way. I would say that this is not blank, but if you put the points from the observations, they would disagree with each other. So I think what is very important, because there are estimates in X-ray, but also in the cool CGM of the baryon fraction in galaxies. Between 10 to the 12 and 10 to the 13,
the
even
cool
below.
CGM is negligible by mass.
Some authors would tell you that they have all the missing baryons in even one of these components.
So let me update my statement with the recent eRosita papers, right? So there's been stacking papers down to here, actually. Pretty impressive, filling in this regime in X-ray stacking. So I think we're getting very quickly, also with SZ, to the point where we can, have firm constraints down to 10 to the 12.
Okay, one more quick question.
Hey, you were talking about, and I think it's very important, the magnetic fields when you're talking about the tentacles in one pressure strip galaxies. And you were talking about exactly magnetic draping and how this helps to form more stars, for example, or could, it could help in the star formation just in the tentacle. So I was wondering why in TNG50 we don't have all the snapshots with magnetic fields. It's just in the full snaps. And I want just to tell you directly.
I apologize.
Because, if one wants to go into the evolution of that, that's why we are working with simulations. There's a gap, a huge gap.
Can you imagine, 8 years ago when we were deciding what is important, what do we really need to save? We said magnetic fields, and who's really going to care? So we didn't save them very much. It's a technical detail. Yeah. Thanks.
Okay, our next speaker is Kraljic. She is going to tell us about the coevolution of galaxies and the cosmic web over cosmic time. Okay, so hello everyone. Let me start as well by thanking really warmly organizers for the kind invitation. It's really a great pleasure to be here, and so far it's really an excellent conference. So I guess we are going to move slightly on larger scales, as in this talk I would like to give you a really brief overview of the recent advances in the field of galaxy evolution, purely from the perspective of large-scale structures, which is this very spectacular feature seen which is this very spectacular feature seen in the distribution of galaxies in our universe, but also in the distribution of gas and dark matter as seen in the numerical simulations on these large megaparsec scales. And such a distribution of matter was in fact observed for the first time more than 30 years ago now. And it was this celebrated map of the first CFA redshift slice that really provided an initial hint about the existence of the cosmic web. And in forthcoming years, this view has been quite dramatically expanded thanks to surveys such as 2DS, or even in more spectacular way, SDSS. And since then, these and literally all other large galaxy redshift surveys have clearly established that galaxies in our universe are not randomly distributed, but are rather located in these dense and compact groups and clusters, less dense filaments and walls, that themselves surround these vast, almost empty regions called voids, all of which are today considered as basic structural components of the cosmic web. On the side of theory, numerical simulations have shown that this web-like cellular pattern can naturally arise through gravitational instability, with the emergent structures growing from these tiny density and velocity perturbations that were generated in the primordial universe. And this ever larger and more sophisticated numerical experiment clearly demonstrated that such a distribution of matter is in fact a typical manifestation of gravitational instability. So on large scales where the gravity should be the dominant force, its net cumulative impact can be separated in two parts. So the first one is this traceless part of the Hessian, which is directed at the definition of the tidal tensor, and it is this part that will apply distortion and rotation to forming galaxy. And the second part is the trace, or the scalar part, which is directly related to the local density through the Poisson equation. And in fact, it was this scalar part that has been quite extensively studied in the past, giving rise to various scaling relations or the correlations, such as, for example, between the mass and the density, between the star formation activity density or morphology density, which are very well known from the studies of this very particular cosmic web environment, which is galaxy groups and clusters. However, the role of the other components of the cosmic web in shaping the properties of galaxies has only recently started to gain full attention. And this is not that surprising, and in fact there are several reasons for that. So first of all, these large-scale anisotropic environmental effects are the second-order effects, so they need to be first distinguished from the effects of stellar mass and density, which will typically dominate, and it's very hard. And there is a second reason, which is quite recent development of multi-scale algorithms based on the advances in the field of computational geometry and topology, allowing us today study the formation and evolution of structures over multiple scales. And here is an example of one of such tools that is directly applied to the distribution of galaxies in one of the fields of the gamma survey. So you can see in this white colors the filamentary network at the intersection of individual walls shown with different colors. And they nicely show how these walls surround this underdense, almost empty region, so devoid of galaxies, that we call voids. So now, having the tool that allow us to coherently identify all the components of the cosmic web, allow us to define the so-called cosmic web metric, in which galaxies can be assigned a series of different distances. So for example, the distance to the closest filament or the distance to the closest wall, that can then be used to parameterize the effect of this particular environment on different galaxy properties. Additionally, we can also use a purely topological quantity such as the connectivity of the cosmic web, which is simply the number of filaments that are connected to the nodes of the cosmic web located at the intersection of the filaments, and that's where most of the massive groups and galaxy clusters reside. Okay, so what have we learned so far about the impact of the cosmic web on galaxy properties? So let me start by considering the scalar properties and in particular the effect of filaments and walls relative to the effects of high-density nodes. So by looking at the probability distribution function of the distances of galaxies to their closest filaments, it was found that the more massive galaxies tend to be located closer to the filaments of the cosmic web compared to their lower mass counterparts. And this measurement has been consistently done from very local universe, so really low redshift, up to redshift of about 0.9 as captured by the Cosmos survey. And this so-called mass segregation is consistently found also in different hydrodynamic cosmological simulations. So let's move beyond the stellar mass. It was also found that galaxies that are passive tend to be located closer to the filaments of the cosmic web compared to the star-forming galaxies at the same stellar mass. Again, this measurement has been observed or confirmed by observations from really nearby universe, so the very low redshift universe, up to redshift of about 0.9. And interestingly, it's also consistent across different cosmological hydrodynamical simulations. And as Dylan was saying, so in this sense, it's interesting because all of these simulations model quite differently their star formation, stellar, and AGN feedback. And this effect is also felt not only by satellites, but also by centrals. So this stellar mass and specific star formation rate or color segregation has been also identified with respect to the walls of the cosmic web, so which are the even lower density environment than filaments. So again, more massive or passive galaxies tend to be located closer to the walls of the cosmic web compared to their lower mass and star-forming counterparts. The measurement at low redshift is again qualitatively consistent with the measurement in hydro simulations. So let's move further. Central galaxies in the local universe at given stellar and halo mass that are located closer to the filaments and walls of the cosmic web show higher stellar metallicity. They tend to be older and they are more alpha element enhanced compared to the galaxies that are located further away. And what is interesting is that the amplitude of this signal for the filaments and walls in many cases seem to be comparable to that of nodes, which are these high-density environments. Again, there is a qualitative agreement with hydrodynamic simulations. Now, so the last scalar property probably most relevant for this conference, the scatter of the stellar mass and gas phase metallicity relation also shows some dependence on the distance from the filaments and nodes of the cosmic web. And this effect, where galaxies that are located closer to the filaments and nodes tend to have higher gas phase metallicity, is clearly effect of this anisotropic cosmic web environment as it goes beyond the stellar mass and the local overdensity. So again, this low redshift measurement has been qualitatively confirmed in hydrodynamical simulations, allowing us to explain these observations by realizing that galaxies that are close to filaments and nodes tend to have reduced access to the accretion of low metallicity gas that could dilute their metallicity, but also by observing that these galaxies that are located closer to these features of the cosmic web experienced much more active star formation history in the past, meaning that they have enriched their interstellar medium by more metals compared to the galaxies that are further away. Okay, so far I have been focusing only on one-dimensional gradient, so every time considering only one component of the cosmic web. Ideally, what we would like to do, multi-dimensional analysis by considering the cosmic web in its totality. However, for this we would need much larger number statistics. Sort of a first attempt to this multidimensional analysis is this result of the fraction of red or passive galaxies as a function jointly of distance from the filaments shown on x-axis and the distance from nodes shown with different colors. So we can see is that the fraction of red galaxies increases at the fixed distance from the filaments as we decrease the distance from nodes. So as we go closer to the nodes of the cosmic web, red fraction increases. This is not surprising, and in fact, it reflects the well-known relation between the star formation activity and the density, which is known for galaxy groups and clusters. What is, however, interesting is that this radial increase in this red fraction at the fixed distance from the filament, but also at the fixed distance from the node, this fraction increases with decreasing distance from the filaments. So this suggests that there are some physical processes that are operating on galaxies and modifying their properties before they enter really the virial radius of these massive halos. Okay, so can we understand the existence of all of these gradients in some theoretical framework? And the answer is yes, at least partially, and hints are coming from the excursion set theory. So quite relatively recently, Musso et al. Revisited the excursion set theory by conditioning the excursion to the vicinity of the large-scale filaments. And without going too much into details, the result of this computation can be summarized on this plot, which shows the different isocontours of predicted mean density, typical mass, or accretion rate in the reference frame of the saddle. So this saddle point is sitting here at the origin, the direction of the filament is outward, upward, and the direction towards the void is to your right. And in fact, what you should take away from this figure is that all of these isocontours are explicit and distinct function not only on the radial distance from the saddle point, but also the orientation with respect to the filament. So this is the math when you do the calculation. However, what does that mean physically? It means that these tides, large-scale tides imposed by these large-scale filaments will impact the assembly history of halos in a way that depends on the geometry of the saddle. Okay, so this theory, strictly speaking, applies only to halos, and there is still not clear consensus how to apply this directly to galaxies. So what we can do, we can go back to hydrodynamical simulations, and we can stack the galaxies in the reference frame of the saddle point. So the saddle is here sitting at the origin, z-axis is the direction of the filament, and the two remaining axes are the major and minor principal axes of the inertia tensor in the vicinity of the saddle point. So we have this three-dimensional structure around the filaments, and what we can do now, what we can do, we can cut the planes in the longitudinal direction along the filament and in the transverse direction, and simply measure the isocontours of different properties of galaxies. So let me show you one example. So here is the longitudinal and transverse isocontours of the stellar mass of galaxies, and we clearly see that they show the radial and angular dependence in this reference frame. So again, the saddle point is sitting at 0, 0. This is the direction of the filament, and the crosses are the nodes or the highest density regions. So again, we can note that the saddles are in fact the local minima in the longitudinal direction, so the stellar mass of galaxies increases from the saddle point towards the nodes, but in the transverse direction they are local maxima, meaning that the stellar mass of galaxies increases from the voids towards the filament. Okay, so going beyond the stellar mass, we could obviously measure all other properties of galaxies, and we did, such as, for example, the specific star formation rate or other properties that you can think of. And here I would like to a little bit stop for a while and recall that I think, or I hope, that we are really going slightly away from this old paradigm where people thought that the only thing that we need to know in order to understand the properties of galaxies is their halo mass, and if it doesn't work, well, that the local density, okay? So here I'm showing the isocontours of these two quantities for a particular stellar mass beams, again in this reference frame, and how we can test this idea, whether the halo mass plus local density is enough to explain other properties of galaxies. What we can do is to define a sort of mapping function that takes these two parameters, so the halo mass and the density, and map it to the property of galaxy that we are interested in. So for this exercise, I will be using the V over sigma, so the rotation over dispersion dominated velocity, and you can think about it as a proxy for morphology. So once we have defined this mapping function, we can compute such isocontours in this reference frame for this particular quantity. And then we can subtract this from the one that we actually measure in the simulation. So what we obtain is this map of the residual. So there are two things to note. They are not zero. And the second one, that they show a very particular geometry, and this geometry reflects simply the geometry of the saddle, okay? So halo mass and density are not enough. So what could be the additional property that can explain, at least to some extent, what drives these residuals that we see in this reference frame? For a few seconds, I will try to convince you and argue that it's the spin advection. So we have been hearing about this during not only today, but also the last past days. And we know sort of that the angular momentum advection is governed by the large-scale tidal tensor. And these induced tides by the presence of the large-scale structure will not impact only the accretion and merger history onto the halos, but also the filamentary flows of the cold gas, and therefore all the properties of galaxies that rely or depend on the cold gas, meaning the star formation or even their morphology. It was also shown that galaxies in the vicinity of the filaments, which are the vorticity-rich regions, and this is the measurement of such vorticity in the vicinity of the filament, those galaxies that are sitting in this region will accrete or acquire the angular momentum by a quasi-polar accretion of the gas with their angular momentum aligned with the filament. And this accretion is expected to be most efficient if really the angular momentum is aligned with the preferential direction of the infall, which is filament. Okay? So our interpretation of this excess that is seen in these residual cards or maps is that it's the signature of the efficient or the maximal accretion of the cold gas or the spin advection, if you wish. Okay, this brings me to another kind or class of properties of galaxies, so the spin properties and in particular the angular momentum. So I will just highlight a few results that I think the community converge onto. So hydrodynamical simulations and different types of simulations, so it does not depend on the code that you are used, converge on the fact that the angular momentum orientation of galaxies with respect to the filamentary structure depends on the mass. So the low mass galaxies have preferentially the angular momentum aligned with the direction of the neighboring filaments, while the more massive galaxies tend to have their angular momentum in perpendicular direction. This has been seen previously for dark matter halos. And what is interesting is that there are some signatures that confirm this kind of trends also in observations. So mainly in a low redshift universe, where it is found that the late type galaxies tend to have their angular momentum aligned with the filamentary structure, whereas the S0 galaxies tend to have their angular momentum in perpendicular direction. There has been some tentative measurement also of this transition mass. And exactly the same thing happens for the walls of the cosmic web. So again, hydrodynamic simulations showed that low mass galaxies tend to have their spin aligned with the direction, or they have their angular momentum, aligned with the wall of the cosmic web, whereas more massive galaxies tend to have their spin in perpendicular direction. Again, confirmed by different simulations seen for dark matter halos, and all this is consistent with the conditional tidal torque theory on how the forming structures acquire the angular momentum. Again, there was a tentative measurement of the transition mass for this in SDSS. Okay, let me now move to nodes, and I would like to go back to this property that I was mentioning earlier, connectivity, which is simply number of filaments connecting to the node of the cosmic web. This property is really interesting because it is a natural probe of the growth of the structure. Okay, think only about the filaments as the dominant channels of transport of not only the matter, but also of angular momentum to the galaxies. So I'll be showing really few only results obtained using different hydrodynamical simulations, but more importantly, in my point of view, also the data, so from the local universe SDSS. Okay, so let's have a look at some results. So on this panel, I am showing the probability distribution function of the connectivity as measured for the galaxies that are sitting at the nodes of the cosmic web for all of these three samples. So real data and false, very wrong simulations. So all three models show very qualitatively similar distributions of connectivity. This arrow shows the median value, which is the same for all of the three data sets, and the mean value is also very close to 3. So this means simply that on average, galaxies tend to be connected to 3 dominant filaments. Now, this connectivity depends on the stellar mass. So as we can see, and again in qualitative agreement between different data sets, this connectivity increases with increasing stellar mass as expected. So more massive galaxies or more massive halos tend to be connected to more filaments. Now let's go beyond the stellar mass, and we can do the same exercise by now splitting galaxies into passive and star forming, and this is directly measurement from SDSS. And what we find is that at fixed stellar mass, passive galaxies tend to have slightly higher connectivity compared to their star forming counterparts. And we can do this measurement in terms of the residuals of the specific star formation rate at the given stellar mass. And again, we see the interesting thing that galaxies that have higher connectivity tend to have deficit of specific star formation rate compared to galaxies with lower connectivity that have excess of specific star formation rate. The same thing is seen for morphology. So galaxies that have elliptical or S0 shapes tend to have higher connectivity compared to spirals or irregulars. And just to show you, this is the measurement from high dynamic simulation. So you see that there is a quite good qualitative agreement. Okay, because we have simulations, we can have a look at the impact of the halo mass. So what I'm showing here is the connectivity as a function of a halo mass for different galaxy properties split in highest and lowest quartiles. So what we have found is that at a fixed halo mass, galaxies with higher connectivity tend to be more massive in terms of stellar mass, tend to have a lower specific star formation rate, and tend to have a lower V over sigma, so tend to be more elliptical. Okay? So while the results on the stellar mass and probably on the V over sigma do not seem to be very surprising, simply means that as you have more filaments and more matter can be accreted onto the galaxies, well, these galaxies will be more massive, and galaxies with being connected to less filaments can accrete more coherently their angular momentum. What is really surprising is this result with the specific star formation rate. Because naively, at least at higher redshift, one would expect that more gas that is, or more matter that is accreted onto the galaxy would result in higher star formation activity. But exactly the opposite is seen at low redshift in this measurement. And one possible explanation is that, in fact, more gas driven onto the galaxies means at some point that black holes will trigger the AGN feedback. And this is in fact confirmed by comparing these results from Horizon AGN. We have exactly the same simulation but without AGN. And in fact, there is almost no difference between the specific star formation rate dependence and the connectivity. Okay? Now, in a few remaining minutes, I have a few slides on conclusions and perspective. So what I would like to maybe pass as an important information from this community is that what is the state of the art in terms of mapping of the cosmic web in our universe today. So far we have been able to map the cosmic web from very low redshift up to redshifts, let's say, of about 0.8 using the spectroscopic surveys. However, these at such a high redshift, we need to rely on photometric surveys, that allow us to reconstruct cosmic web, but only in 2D. Going beyond the redshift 1 is impossible with the current photometric surveys because they are not deep enough. And then at very high redshift, so a redshift of about 2.5 and 3, we have access to the underlying density field through the tomographic reconstruction of the Lyman alpha forest absorption of light from bright background sources such as quasars of bright galaxies. And there is this window between the redshift of 1 and 2 where we have absolutely nothing. And it's really sad because that's where the cosmic noon is happening. So all the interesting things are happening. But as someone already said this week, the future is bright. And so this will change very soon thanks to surveys such as Euclid or MOONS on VLT or PFS on the Subaru telescope. So just to give you an idea, so for example, the PFS, so this low Z, so low Z now becomes redshift 1 and 2, will allow us to perform analysis, SDSS-like analysis of large-scale structures, but now at the redshift between redshift of 1 and 2. So here is just an example of the predictions made for the PFS of the walls and the filaments of the cosmic web within this redshift window. So I have been showing you several types of what I call the segregation and the alignment of the angular momentum of galaxies with respect to the filaments, but also with respect to the walls. And the few last seconds that I have, I would like to highlight something that I thought could be very interesting for this audience. And this is the impact of the walls. Remember, so these are the even lower density environments than filaments that may have an interesting impact on the content of galaxies. So this is what I'm showing here are sort of zoom-in simulations of the void regions, but we don't care about void, there is nothing interesting. So we care about the walls that are surrounding these voids. And it was found in these hydrodynamic simulations that some halos could have really difficult times to accrete external gas. And this halo, and it is because they have this fast-flowing material around them. And these halos happen to be, these are these red dots, these halos happen to be in the vicinity of the walls. And if you look carefully at these arrows that are attached to them, which are simply the relative motion of the gas with respect to the halos, they all point towards the walls. So we were scratching our heads around a little bit because we didn't understand it at the beginning, but it's crazily simple. You just need to think about large-scale structures and how the flow of the matter inside the large-scale structures is happening. So here is an example of that wall, and you have voids on each side. And so these gray arrows are showing how the gas is moving. So we know that gas is expelled from the voids towards I'm done in a few seconds, towards the walls of the cosmic web, and the galaxies or halos are moving with them. And so if the halo is located in this region, so in this first void, it will move along with the flow. So the relative velocity will be very low, and this halo could in principle accrete the ambient gas. But once this halo crosses the wall, it will still continue to move in that direction, and it will encounter the gas in the opposite direction. This is exactly what is happening in galaxy clusters, okay? So the round pressure stripping and so on and so forth. So in this case, the relative motion is really high, and it's much higher than the escape velocity, and therefore these halos or galaxies in them will have really hard times to accrete the gas. And in fact, if you look at the gas structure, we see this sort of, it's very bad resolution, but it's like jellyfish-like morphologies due to the round pressure stripping. And I will stop here. Thank you very much.
Thanks very much, Katarina. This was great. I wonder, all the results you were showing from the simulations were at low redshift, right?
Mostly, yes.
Do you think that the importance of the cosmic web on affecting galaxy properties in different locations, I mean, it could either be due to gravitational effects like the tidal effects, or it could be due to the gas dynamics and gas, heating and shocking within elements of the cosmic web. Do you think that which of those two is more important changes across redshifts?
Yes, so this is a good point. So the dependence on the redshift, I think it's an important part. So for example, so it's true that I was showing the results mostly for redshift 0, but obviously, as you can guess, we did have a look at a few of those properties at higher redshift. So there seems to be a sort of qualitative consistency between the redshift 0 and redshift 1. However, at redshift 2, things start to change. Now, I believe that what is really important is our understanding of really baryonic physics. And it may seem as really a stupid phrase, but the thing is that we need to model properly what the gas is doing. Otherwise, it doesn't make even point to compare with observations, because, for example, all of these large-scale cosmological hydrodynamical simulations, which are really excellent and great, and I am a simulator as well, so it's not that I want to say something negative, but none of them is able to reproduce, for example, the SFR function. So this is something that we usually do not compare. We typically look at the stellar mass functions and we say, it's sort of okay. But the SFR function up to redshift of about 2, there is no of this simulation that is able to reproduce the observed values across the redshift. I'm not talking about a particular redshift, right? At redshift 0, some simulations do a quite a good job. Other simulations do an excellent job at higher redshift, but none of them is able to cover the total range of this redshift. So Yeah, I think the gravity is the dominant force, as I was trying to convince you. On large scales, gravity is there all the time. But at the different times in the evolution of galaxies, and this is most likely also a stellar mass dependent statement, at some point our understanding of baryonic physics start to be really crucial.
Hey, Caterina, thanks a lot. So I fully agree with you that environment is multidimensional. We shouldn't just do MLO, density, etc. But then from an observational point of view, it seems now that most of these works that both look at the variation as a function from the distance from the spine and the alignment, just look at that quantity, don't take into account whether the galaxy is a satellite, whether it's in the group, and how the group affects that. So can you comment a bit on this, on whether from a simulation point of view, you can put upper limits on the relative effects?
I think that this will also depend on what environment of the cosmic web we are talking about. I think I would totally agree with you that once you are in the cluster environment, well, if you use density, you are pretty much using a good parameter, right? The point I want to make here is that we should not forget about even larger anisotropic environment, okay? And it's true that satellites and centrals, it's a little bit tricky. At some points I tried to highlight that satellites also feel this kind of effects, the alignment as well. I mean, there are some features that I could give an entire talk about that. Clearly, there are some differences. So we need to pay attention whether we talk about centrals on satellites. Often in observations, it is extremely difficult. So when we want to compare, even though it's totally not apple-to-apple comparison, because we just cannot do that, there could be differences. Okay.